So wake me up when it's all over.
We saw how well that quadratic fit on the data in the last video, but we also saw that without the x term, it looked like it fit okay. I think the residuals were improved. So how do you pick the right model? So let's read in our data set just the way we did before, and let's come up with a whole list of ideas of types of models we might try. So here's a bunch I think we want to try. Let's go with linear, which we saw last time. We'll do a quick recap of why it didn't work. Here's the model where we had the x squared without the x. We also saw that in the last video. And then the quadratic model that did work. And while we're trying different forms of the quadratic, let's talk about if we didn't have that y-intercept. And since the quadratic worked, let's try the cubic and the quartic, and we could go on to the quintic, and we would probably not go further because of weird names, but let's talk about what happens if we go higher in polynomial than what's actually needed. So these are going to be all our polynomial models. Here we're going to try a square root, which kind of bends, but it won't bend nicely. Log model, and I'm going to specifically leave it just as this, even though a more fine-tuned type of log model might actually fit the data a little bit better. But we're going to see this kind of model later, and so I want it in the back of your head that you've seen it. And then, just to show that we can, let's do something crazy, and we'll go through each of these pretty quick. Starting with that linear model, in the residual plot, the very first one, we see this gentle curve, which suggests we really ought to try it, and then when we did try it, we decided it was a good idea. So then we went to a model that just had x squared, because we were showing that x didn't pop in automatically on its own. But in the residual plot, it actually looks pretty good. I mean, this convinced us that maybe this was an acceptable model, and the summary had good results, small p-values, and actually it had a small standard error in r squared, kind of as good as we could hope for. The only reason why we didn't end up, give me my plot, there, is there's one section here where it looks like the line bends up, and it really should have bent in just a little bit right here. Plus, you really should try x if you're going to be using x squared. I don't want to have to write in my report the reason why I didn't use the x squared, so it makes more sense that I would have thrown it in just to try it, which is how we ended up with this quadratic model. And this model had great looking residuals. I don't see any problems or issues. I wish real data would end up that nice. And we looked at the summary to get our prediction equation, which we could plot, and that seems to fit the data really nice. So I'm going to say this is definitely one of the models that does fit the data well. But since we're playing around with different forms of this quadratic polynomial, is there a way to kill the intercept? And we have never talked about it before, but there actually is. If I say a -1, this is a constant term, that's going to kill my intercept. And I hope nobody asks what happens if you do that with categorical data, because we're just going to run this and then look at our residual plot and say, oh, that's not good. That's not, do you see the pattern? Do you see this double wing-like shape? And why is it doing that? Well, I think you'll be able to see if we look at the plot. Oh, there's the summary. Notice that intercept term is completely missing this time. And there's what it looks like. If you've restricted the types of quadratics you can use to where they're not allowed to be an intercept that moves, then you're not allowing it to have all the kinds of quadratics that it needs. So, bad idea. That's why we're not really going to play with that, like, ever. Some programs don't even allow that option. So if we've played with a quadratic, what happens if we add a cubic? Well, that's easy to do. Cubed. And I was trying to do a summary, but see, this is the problem with trying to plot those residuals is now I have to scroll through each of these. Yeah, okay, it looks fine. Let's look at that summary, and right there we hit a problem. See, the data says that cubic term really is not helping. And we can do a prediction equation. It doesn't fit on one line for me, so I'll spread it between the two lines. And hang on, I gotta start with the plot. Does that look any different than the quadratic? Well, hang on. I can actually do both of those at the same time. Here's before, here's after. Before, after. I can actually barely see a jump. I'm willing to bet that the resolution in the video you can't see any different. But notice for this cubic model, our residual standard error is still just as good. Our R squared is 0.7938. And with the quadratic model, it was 0.7936. So R squared has gone up. It's not enough to be worth it, and that's why we don't look at R squared. So the fact that that cubic term had a p-value that was above 0.05 suggests we don't need a cubic in there, and that's not surprising if you look at the picture. So what do you think is going to happen if we go to a quartic model? Let's go through the residuals real quick. Oh, look, they don't look any different because the quartic model has as a special case the quadratic model. And if we look at the summary, that quartic term is not significant, 0.3, but having those extra terms in there has made the model all confused. What is it you're trying to do? Look at all those p-values. Nothing here is significant. That's the danger of throwing junk in your model. Look at the R squared, 0.794. It's gone up just a little bit. To remind you, what we had before was 0.7936 and then 39, and now 0.794. R squared says, hey, yeah, I like this. But no, come on, you had to know this wouldn't help. So we don't need that quartic term, and it's made all the p-values go bad. We don't want to do this. Should we look at the picture real quick? Let's put back the picture that we had when we had the quadratic right here. Nope, that obviously was not a quadratic. That's our intercept missing one. Let's put in the quadratic there, and let's try what happens if we have a fourth model, which is the age. Age, really? I need age hat on all these. I specially called it age hat instead of age so that I wouldn't get confused. By the way, this term here was negative, and so that's where that negative comes from. It's not here because I need R to know that there's more coming in the next line. Okay, so here's before, after. This feels like the eye doctor. Which one looks better? Plot B, plot A. Plot B, plot A. Doctor, they look exactly the same. So keep in mind that if you have too many terms on your polynomial, you should back them off and do it slowly. This relates to an issue called multicollinearity, how a piece of junk in your model can mess up all the other p-values. And when we hit multicollinearity, we'll talk about going through deleting terms one at a time. Let's go to some crazier models like the square root. And there do exist some real-life scenarios that have a square root function. Residuals. I neglected to see the first plot. Did we, oh, there it is. That doesn't look too bad. I'm a little bit surprised. I really thought they would look crazy. I guess that's why I wasn't sure if I had residuals or not, because I expected them to look worse. Now I'm all curious. Does this fit? Hey, that's not bad. That's really not bad at all. I want to see the summary here. I'm going to be a little surprised. I didn't expect this one to work out. Very significant p-values. A nice fit to the curve. All right. I'm going to say, as much as I'm surprised, good residuals, significant p-values, and pretty decent results here. 9.945 and 7.923 on the R squared. Just so that you can remember when we did the quadratic, 9.914. So our S is a little bit higher, but enough to matter. The R squared is a little bit lower, but not a whole lot. I'm going to say this is a good model. Now, I'm not super comfortable describing square root functions, but it does happen in real life, and this might be a good function. If some student chose this to describe the data, I would say that was perfectly acceptable. Although I myself, I think I would go for the quadratic because I'm more comfortable with quadratics, that's all. Now let's throw in the log, and I'm not going to spend a lot of time on this because we're going to do it in an entire chapter, but notice I did not need the interpretive statement. You could actually use it and it wouldn't matter. But the residuals No, I'm going to say that's not okay. That right there is enough for me to stop. But since we already did all the rest of this, let's look at the summary. Sure, they're all significant. Having all the p-values significant is not enough to say it's okay because of that residual plot. And no, that is not going through the data quite the way I think it really should be. I'm going to say that this isn't the right data set for a log. And we will, when we get to it, see what kinds of data sets are right for a log. And now, something crazy, just to show that there's almost no limit to what you could do. I want a sine of x function. If you've had trig, you know what that is. X is age in this case. Plus just age normal, that's for my beta 2. And then next I have whatever you call this. It's a log of 1 plus age, because that's what my x value is, divided by the tangent of age. I have no idea what this is going to give me. I sure don't want to try to explain it. I really hope this doesn't turn out to be a good model. Let's look at the residuals. Well, I expected it to be worse. There's a little bit of curve there that I'm not happy with. Let's take a look at our summary. And because this name is so huge, it has pushed it onto multiple columns. I'm afraid to squish my window because I'm afraid I'll crash R if I do. I need to squish it more. Please don't die. It died! Maybe. Oh no, we're okay. I might have had to pause the video so that I could yell. Actually, only this guy was the one that was ridiculously not significant. Let's make my plot window larger again. And I want to see what that picture is going to look like. Object age not found. Hang on. We got to make these age hats. Okay, try it again. Yeah, that looks pretty weird. There's a little tiny red spike right here that's somehow picked up. I don't even know what it's doing there. That doesn't quite seem to fit the data, but it's not as bad as I thought. It makes me curious and that I want to try a trig function. I pulled out my trig book and I think this actually might do it. So I really should pause the video for this in case it goes poorly. The sine of x minus 1. Is that right? Because that way my curve will be shifted over on top of 0. Well, let's give it a try. Object x. Oh, that's because x is age. This is why you pause the video. Okay, yeah, alright. I don't know. I think I liked the residual plots before better. I do have significant p-values here. This p-value is small and so is that one. Let's see what it looks like on the picture. I gotta change to match my prediction equation. No. So I'm going to say, no, I don't think a sine function is the right thing here. But that's unless the client comes and says it really should be a sine function. And maybe what I would do is show them this picture and say, are you sure about that sine function? Maybe it's a sine function plus an x squared or something. Let's talk about the theory behind this and we could go more into it. So here we've played with a whole bunch of different models. We actually found more than one that worked well, and surprisingly we found 2 that it would be perfectly acceptable. And I'm going to pick which one I want because of how comfortable I feel about describing square roots versus quadratics. But in your data sets, if you find a good function and you can explain it and talk about it, that's what you should go for. In the next video, let's talk about how we would explain this to a client in a report.